Let's talk about the pH of polyprotic acid. So polyprotic acid, poly means many, protons, acids with many protons. So H2SO3 has 2 protons that it can potentially give up. As the first one is removed, you're going to have left behind its conjugate base, which is H. There's used to be 2, you take away 1, now there's 1 left, SO3, and that proton leaves the electron behind. That Ka is 1.7 E negative 2. That's pretty significant. Then this HSO3 minus could potentially give its H plus as well. And you're left with, remove this H plus, you're left with the SO3, and it used to be negative 1, but this H left another electron behind, now it's negative 2. That Ka is very small. Okay, now what does that tell you? That tells me that this reaction is not very significant, which means the equilibrium wants to be, this is products, this is reactants. It doesn't make too much product, so this is very little amount of this. That means you're going to have more of this. Okay, so if I had H2SO3 in a beaker, I imagine it to look like this. A lot of some H2SO3s left because it's not a strong acid. There will be some H pluses in the beaker as well. There will be some HSO3 minus, and there will be hardly any of this substance. Okay, that's what that means. So I'm not even going to put it in the beaker. It's just very, very little of that. So you should imagine this happening in the beaker. Okay, it says that the difference between the Ka value for the first one, this number, is very different from the second one, 10 to the negative 3 difference. That's like 10 to the negative 6 difference. Then that means then the pH is generally depends on the first dissociation. So when you're getting pH, do you think you should add this H plus that you make when this broke apart and add it to this H plus that you made when this broke apart? Added those two numbers and you'll get the pH, or the amount of H pluses and then the pH. Yes, you should do that, but what they're showing you is a trick. If the number, they're very different, which means this is hardly any, which means the pH is pretty much due to the first dissociation. Okay, so let's go ahead and look at these acids. So we have 10 to the negative, we have a H2, these two come off. The first one is negative 3, the next one is negative 12. That means the second H is barely going to come off, not really going to come off. Here, the same thing. That second H is not going to come off. Really small. Citric acid, it has 3 H's. The first one, it'll come off a little bit. Yeah, you're going to get significant there, but the second one, not too much. Okay, and so on and so forth. Okay, so let's do a sample problem. The solubility of CO2 in water, in pure water at 25 degrees and 0.1 atm pressure is this. So when you blow some CO2 in water, you're going to get this much dissolved. Okay? This acid, when you put this in water, it combines with water and makes carbonic acid. Okay? The carbonic acid will then dissociate into H plus and HCO3 minus and cause your solution to be acidic because you have H pluses. Okay? If you have 0.0037 here, what is the pH of the solution? That just means if this is 0, 0, this is going to be minus x plus x plus x. 0.0037 minus x. This will be x and x. They're asking, when this is done reacting or done dissociating, take the H plus right here, take the pH, what is that pH, right? And you might wonder, oh my goodness, there's another H. So perhaps this H, CO3 minus, can break apart as well, right? Into H plus and CO3 minus 2. So you have two H's. Here's the next one, right? How much H will you get from that? Once you get that H and this H, you can add them up and get the pH that way. So let's try it. So first, I need to get the Ka of H2CO3. So they didn't give it to me in the problem, so you must check the appendix. Okay, Appendix D has H2CO3 somewhere right there, carbonic acid, 4.3 E negative 7. The second one, 5.6 E negative 11. That's a difference of 4, 10 to the negative 4. That means the second one is barely going to come off. So let's first deal with the first H+, 4.3 E negative 7. So this is Ka is equal to 4.3 E negative 7. Okay, so let's change colors here really quickly. So Ka is equal to H plus, HCO3 minus, and H2CO3. Okay, then I'm going to plug in 4.3 E negative 7 is equal to x times x, which is x squared, divided by, this is going to be negligible. Look at that, negative 7. That's really small. So 0.0037. Solving for x is equal to 4.0 E negative 5. And that is the molarity of the H plus. So that is x right here. That's this number and also this number, okay? They're both that number, okay? So this number, 4.0 E negative 5, is going to go here. That's what you have in the beginning, 4.0 E negative 5. So again, when the 0.0037 is put into water, it makes H plus and HCO3 minus. You get this much of H plus, and also, where else? This is there as well because that's already in the beaker from the first dissociation. That's your initial now. Does that make sense? And you have none of these yet. Okay? So again, you started with 0.037 minus x plus x plus x. This is what you make. And you made that of the H plus, and which is the same as 4.0 E negative 5 molar of the other substance, HCO3 minus. So I put those numbers in here, okay? That's your initial. Now this is going to break apart. Minus x plus x plus x. 4.0 E negative 5 minus x. 4.0 E negative 5 plus x, oops, negative 5 plus x, and x. Okay, Ka here is given in the chart. It was the number that's really small, right? So H2CO3 is 5.6 E negative 11, really small. So you know it's barely going to happen. Okay, 5.6 E negative 11. Okay, so you know this is barely going to happen, and you know that this is barely going to happen. Okay, so now when we get the Ka, it'll be 5.6. I'm sorry, just write the equation first. I always write the equation just to show you guys what I'm plugging in, okay? Ka is equal to this H plus, this CO3 minus 2. So it's the second dissociation, which you know is not going to be really significant, right? And HCO3 minus. So Ka is 5.6 E negative 11 is equal to H plus is 4 E negative 5. The X is gone. This X is here. And this is 4.0 E negative 5 as well. Okay. So when solving for X is equal to, this cancels mathematically, which is 5.6 E negative 11. That just equals to 1. This is the X. Okay, what did I just find? This is the amount of X that you need to, that dissociates from HCO3 minus. Did you get a lot of H pluses? No, this is the amount of H pluses that came off. That's this X right here. That's this X right here as well. You hardly get any of these two things that came apart from this substance. That's the bicarbonate ion, by the way. Okay, so this is the amount of H plus. You add this number to what you got in the beginning, which is that from the first dissociation. This is from the second dissociation. You add them up, and you're going to pretty much get this number, 4.0 E negative 5. This is the molarity of H plus. Because when you add this number and this number, go ahead and add it, you'll get this number because this is negative 11. Okay, so to get the pH, you just take the negative log of this, which is negative log of 4.0 E negative 5, which is equal to 4.40. Okay, so what does that mean? If you take H2SO, if you take H2CO3, this molarity is what you have, and you put it in water, your pH will be 4.40, and that's mainly due to only the first H coming off, because the second H coming off was really, really close to 0. It was hardly anything, 5.6 E negative 11. And the reason that is if you look at the Kas, they're very different. They're like different by -7, -11, by -4, 10 to the -4.